Listo, estamos en vivo.
Okay, gracias. No, let me present you so we can start. Well,
Certainly.
Hello, everybody. Thank you very much for attending the Tartaglia seminar. Today, on the 17th of November of 2022, we have the honor of having Tomas Persson with us. Tomas is a researcher at Lund University in Sweden. His main areas of expertise are fractal geometry and especially some parts of dimension theory in the sense of fractal geometry, not topology, and also shrinking target problems, recurrence, and Borel-Cantelli type problems. Today he will talk about recurrence, and we kindly thank for his talk.
Thank you very much for the invitation and for coming to listen. So I will talk about recurrence. So this is a classical subject in dynamics. I'm going to say a few things about classical results, and then I'm going to say a little bit about less classical results, and then even less classical results. I think most of the people attending are dynamicists, meaning that you know the basics of dynamical systems, but Gerardo told me that maybe not everybody are like that, so I'm going to say just a few basic things about dynamical systems. So what do we have? Well, we have, let's say that we have a metric space, and we have a transformation of this metric space, and this will make up a dynamical system. We iterate this function t. So I mean, I have this is my space x, and I have a point which is iterated by this transformation in some way, and we get the sequence of points in this space, and this is called an orbit. So it's an infinite sequence of points in the space. And what I'm interested in is what is going to happen in the long run and what happened on average. So usually you're interested, or at least usually I am interested in chaotic systems, and these are systems that you cannot really efficiently forecast what's going to happen, but you could take a probabilistic viewpoint and you could say what happens on average. And in order to do so, you have to have something which you can measure probabilities with. And this is done with a measure, and a measure which is called invariant. I call the measure mu. It's an invariant measure, which is invariant with respect to the dynamical system, which is made up by this transformation. And this means that the measure of a set is the same thing as the measure of the inverse image of the set. So suppose now that I'm going to suppose this during the entire talk, that this is a probability measure. Meaning that the measure of the entire space is 1. And then you could think of this relation of the invariance in a probabilistic sense, meaning that if I look at this system during a long time, and then at some point I'm asking the question, what is the probability that this point that I'm iterating, that it ends up in the set A? Well, this probability is supposed to be this mu of A. And what I'm asking here is that the probability that at some moment of time I'm in this set, this should be the same thing as, so if this is A and here I have the pre-image of A. So what I'm saying is that I'm asking that this probability that I land in A at a certain time point, this should be the same probability as being in the pre-image at the time before. So this is a reasonable requirement if you want to have some probability which is stationary in time and doesn't change over time. So that's why you study these invariant measures, and there's the theory about invariant measures. This is called ergodic theory. And maybe the very first result on ergodic theory is by Poincaré. And this is the so-called Poincaré. the Poincaré recurrence theorem. And then I have to assume a little bit more about this space. I'm going to assume that X is separable. And that's symmetric space and so on. And I have this measure, which is an invariant probability measure. And then Poincaré's theorem says that then almost with respect to mu, every point small x, we have the following. If I look at the distance between the nth iterate of the point and the point itself, this becomes arbitrarily small. And one way to say this is to say that the lim inf, as n goes to infinity, of this thing is 0. So when I'm iterating this system, here's my space x again. I have my point small x, and I iterate it, and so on. And eventually, I will come back very close to where I started. Maybe I have to wait for a long time, but eventually I will come back, and I will come back closer and closer. Another way to say this, which I will sometimes use, in particular in the later parts of this talk, is that is the following: that there exists some sequence Rk, which depends on x, on the point I start with, and it decays to 0, such that the kth iterate of x belongs to the ball around x with radius Rk of x for infinitely many k. So when I iterate this thing, I look at these balls which are shrinking around the point x. They get smaller and smaller, but nevertheless I will come back to them infinitely many times if they shrink in a certain way. They cannot shrink too fast, but there is some speed which makes this thing happen for infinitely many k. So that's Poincaré's recurrence theorem. It was actually not proved by Poincaré, but it was proved, or at least the publication of the proof is 1919 by Theodor. And if you took a course in dynamical systems, you probably saw a proof of this theorem. I think I skipped the proof. If you've seen it, you've seen it. Otherwise, you can find it in a textbook anywhere. It's not a very difficult proof, but the proof that Theodor published is the same which you have in modern textbooks. So it's a nice thing. What I'm going to talk about in the rest of this talk is how can we improve on this result. So I'm going to give a sequence of results that are in some sense weaker, but in other sense stronger. I'm going to add assumptions on the systems, and then the conclusions will be stronger. So this is what we're going to do for the rest of the talk, or at least for most of the talk. Maybe I have the time to show a little bit of some application of these results, but let's see. There's a result by Boschernitzer. This is from 1993. This is still a very general result. You assume very little more, but you get a more precise result. So you assume that that the space X is sigma finite with respect to the alpha dimensional Hausdorff measure. I write it like this. So alpha dimensional Hausdorff measure. So for instance, like if alpha is an integer, then you get the Lebesgue measure. So If I have a space which is just a part of Rn, then I can have alpha equal to n. So if my space X is like this blob I was drawing, some two-dimensional thing, then alpha is equal to 2, and the space is not only sigma finite, but finite with respect to this measure. So then the following thing is true, that then for mu almost every point x, we have the following, that this lim as n goes to infinity. So before here, I had the distance between Tnx and x, so the nth iterate and the point I started with, but I can multiply this with n to the power 1 over alpha. So this is something which goes to infinity. This is something which goes to 0. Nevertheless, this limit will be finite. In some cases, it's even possible to state that it's 0. I'm not going to go into this detail when it's 0 and when it's only finite. Another way to say this, if you want to say this in this language of hitting a ball, is that you can say that the kth iterate of the point belongs to a ball with center x and with radius some constant, which you don't really know what it is, divided by k to the power 1 over alpha for infinitely many numbers k. So the difference here between the Bosch-Nitsan result and the Poincaré's result is that here you get some information about how fast these balls can shrink, and you still enter into them infinitely many times. So this is it's a striking result because it's very general. Usually in this business, you have to assume a little bit more about the systems to say precise things. But here you get still something which is actually, I'm going to show that very close to optimal, but you get it with very few assumptions. So let's move into then improvements of this, and then we are going to assume something about the mixing speeds of these systems. I'm going to mention a little bit more precise what I mean with mixing speed. Maybe I can even fit this next result down here. There's a result by Pavelets from 2017. He assumes a little bit more structure. He looks at, I'm not going to say exactly what his assumptions are. He has some assumptions on the invariant measure mu, so the measure mu which pops up here. And he has some assumptions on the transformation. So he's looking at some, it could be in any dimension, at least on some manifold, if I remember it correctly. And so T is basically some expanding system. So it's something. So if I have 2 points, x and y, then when I map them forward, the distance is increased in some way. And for these kind of systems, you have more control of how things, what happens. And he could improve this thing a little bit further. He could add an iterated logarithm. So what he got instead was that instead of only having n to this power 1 over alpha, he got log n then to the power 1 of alpha, and then the distance between the nth iterate and the point x, and this lim inf is actually equal to 0. So it means that you can make this constant here as small as you like, and you could even put the log in there. So it's a slight improvement under some more demanding assumptions. So now we're moving into even more recent results. There is a result which is, and this is actually in some sense the optimal result, but under more strong assumption. So it's a result by Hussein, Lee, Simmons, and Wong. from, I don't think I think I saw it's accepted by ergodic theory and dynamical systems, but I'm sure it's not published there yet.
Oh, excuse me. Yeah, it has already been published.
It has already been published, yes. And
yeah.
I think I saw it online, but maybe not in an issue. This is the archive date, so you're probably right that it's published or something. So let me write 2022 ETDS. In any case, it's a result, and they prove results for various systems that are kind of conformal. If you don't know what I mean when I say conformal, you don't need to worry so much. So it's for various systems, but rather specialized systems. But I'm going to state what the results are for piecewise expanding interval maps, because I'm going to compare their result with another result, which is only for those. So for piecewise expanding interval maps, the result is the following. So what I mean is that I'm working on some interval, and by scaling, I can always assume that it's the interval from 0 to 1. You can rescale things. And this transformation that I'm iterating, it's something which is expanding, but it's only like piecewise continuous or piecewise smooth. So it could look like this, for instance. This is my system. So this is what I'm iterating, and if you have such a system, then it's a well-known fact from dynamical systems that there are invariant measures mu which are equivalent to the Lebesgue measure, meaning that it has a Radon-Nikodym derivative with respect to the Lebesgue measure. And this derivative, so the density of the measure mu, is bounded from above and below. So below is bounded away from 0 from below, and it's bounded. So it's something which is really very close to being the Lebesgue measure. And then they prove the following. So for this particular choice of mu, so then for mu almost every point x, we have that. So now I'm going to state the result more in this form. I think it's clearer to state this result in this form with hitting a ball. So the result is that for almost all points, the iterate k of the point, it enters a ball around x with radius rk for infinitely many k, if and only if the sum of these numbers rk is a divergent sum. So you can say exactly for which rates this is true or not. So in this case, when I'm on an interval, then I have that the one-dimensional Lebesgue measure is sigma finite, or even finite on this space. So in that sense, if you compare it to Bosch-Onitsan, this 1 over alpha is equal to 1. So Bosch-Onitsan say that you can have 1 over k, and 1 over k, as you know, is divergent, but it's not very far from being convergent, the sum. So Bosch-Onitsan is very close to having this optimal result. This is, of course, in a much more specialized setting, but in this specialized setting, this is optimal because it really says if and only if. So you cannot improve on it. I mean, this gives a full solution to the problem of determining when this happens infinitely many times and when it doesn't. I'm going to mention a little bit more of how to look at this from the point of view of the Borel-Cantel lemma, but I'm just going to state one more result before I do that. This is a result by myself and two of my co-authors, Kirsebom and Kunde. It's a result from 2021. So we look at these piecewise expanding interval maps. Actually, what we use is that we use systems which has some particular kind of ergodic properties, which these piecewise expanding interval maps have. So our result is a little bit more general than that, but let's just say that we have the piecewise expanding interval map. Again, so the same setting as before, but we are looking at more general measure mu. So general invariant measure mu. So this is the result of this paper. We get almost the same result, but we get it for a more general measure mu. It's not completely more general, but I will not state exactly what we assume, but we don't assume that it has to be similar to Lebesgue. So we have to change the formulation a little bit. I'm going to explain later a little bit why this is so. But it turns out that to get an optimal result, or to get a good result in the setting where the measure is not like the Lebesgue measure, you shouldn't quite formulate it like this, but you should formulate it in the following way. So I let this RK, which is in the previous result, I'm actually going to let it be a function of the point. And I'm letting it be such that the following is true, that there is a fixed number mk, so a fixed sequence of numbers mk, such that for all x, the measure of the ball with center x and radius rk of x is equal to mk. So what I'm doing is that I'm fixing mk sequence first, and then when I fix the mk sequence, then there is such a radius, unless the measure is not smooth in the sense that it has some atoms. So this is a measure. So this is one of the assumptions I need for the measure, that you can actually do this. But I mean, for most interesting invariant measures for a dynamical system, this will be the case. So this is not a problem. So this is my definition of the RK. And then the result is the following, that if the sum of mk is finite, so this would then correspond to this RK sum over here, would be finite. So it's the sum from 1 to infinity. Then for mu almost every x, I have that tk of x, so the kth iterate of x enters this ball of center x and radius rk of x for at most finitely many k. Finitely many k. So the optimal result that one would hope for is that if this sum mk is divergent, then the iterate tk of x belongs to this ball for infinitely many k. However, we couldn't quite prove that, but we proved something slightly weaker, that if you sum from log n to n, and if you assume that this thing goes to infinity, this thing goes to infinity, so this assumption is stronger than just saying that the sum of the mk's is infinite. But if you have this, then you can say that for almost every x, tk of x enters this ball, belongs to this ball b x rk of x for infinitely many numbers k. So in this case, when this goes to infinity, you have this iterate coming close with this speed to x. So the point comes close to itself infinitely many times. So here there is a gap between the A and B because there are sequences MK which doesn't satisfy any of these A and B. So they are left open. So there's not an if and only if result as in the previous result, but on the other hand, it holds for more general measures. Let me just mention a little bit that this assumption here in B, it's actually satisfied in some nice cases. So if MK is equal to the following, 1 over K times log K times log K, and then if I want, I can go forward and I can iterate the logarithm as many times as I like. Let me say log P is the logarithm iterated P times. Then you can actually easily check by comparing with an integral. You can check that if I sum from K from log n to n, then you can check that this actually goes to infinity. And these things are like very close to being at the boundary of being summable and non-summable. They have a infinite sum, but it's very close to being finite. So this really shows that this gap here it's not very huge, but there is a gap. Okay, any questions so far? I'm going to make a little bit of a comparison with what is called Borel-Cantelli and in particular dynamical Borel-Cantelli lemmas. So let me explain what this is. So you have probably seen the ordinary Borel-Cantelli lemma. I'm going to explain how this dynamical ones are similar to the ordinary one first. So what is this thing about? I mean, there are various ways to state them, but let's say that I have a point y, which is fixed, and I have some sequence rk of radii of balls, and I'm going to consider the ball with this fixed point y as a center and this radius rk. So I have a sequence of balls, and the question that I'm asking is, does tk of x belongs to the ball with center y and rk for infinitely many k? So it's a slightly different question than I asked before, because before we were looking at this question if I had x and y being the same point, but now I'm having a fixed point x, and then I'm asking the question, does the iterate of x enters this ball around y? And the question certainly depends on x, so does the answer. So the answer that I'm interested in would be more likely to be something like for most x, meaning for most in measure. And the probabilities, if we take a probabilistic point of view on this, we look at the probability that tk of x belongs to this ball. Let me just call this bk to have less things to write. So ball k. So what is the probability that I land in this ball? Well, probability with respect to what? Well, say I choose the point x randomly, and then I see if this happens or not. Well, this is actually, so the probabilistic thing is that, okay, I have my invariant measure, so this is my probability. So this is just like the measure of the set of points x such that tk of x belongs to the ball pk. Well, this set is actually just the pre-image, the kth pre-image of the ball. And since my invariant measure is invariant, that's why it's called invariant. As you might recall from the very beginning, and well, if you're a dynamicist, I suppose you know about this, the inverse image has the same measure as the set. So this is just equal to the measure of pk. So the probability that at a certain moment of time I hit this ball, this is just the measure of the ball. And if we now were in a completely random setting where the event that tkx belongs to the ball k, if I look at this for different case, if I assume that they are independent as stochastic processes or stochastic events, rather, then I could use the Borel-Cantelli lemma, which says that this thing happens for infinitely many cases, if and only if the sum of this measure of bk is infinite. So if I look at this set tk of x belong to bk are independent events, then tk of x belongs to bk for infinitely many k, if and only if, and this is the Borel-Cantelli lemma, which says so, if and only if the sum of these probabilities, which is the measure of the ball, if this diverges. So the problem is that if you're doing dynamics, which we are now, they are not independent. So this will not be useful. But you can nevertheless prove these results in many cases, at least if you assume a little bit more or something like that. But there are like results which are dynamical Borel-Cantelli lemma, or called dynamical Borel-Cantelli. And it says that even if these things tkx are not independent, so then they must be dependent, right? Then still this thing for infinitely many k is often, or at least almost equivalent to, I write it like this, that the measure of these things is infinite. I write it like this because sometimes, depending on what settings, in some settings it's really equivalent, and you can actually prove that it's equivalent in some settings. But sometimes you have to be able to prove it, at least, you have to assume that this thing diverges sufficiently fast, meaning like perhaps that the measure should be something like, I don't know, maybe something like I have here or something like that. But sometimes there is a gap between like when this happens for finitely many cases and when it happens for infinitely many cases. But let me just mention, to be precise, one result. And the reason I'm mentioning that result is that I'm going to compare this with yet another result on recurrence that we're going to look at. So there is a dynamical Borel-Cantelli lemma by Kim from 2007. This is certainly not the only and not even the first dynamical Borel-Cantelli lemma, but it's something which is in the same setting as some of the results that we looked at and which we will look at. So this is also for piecewise expanding systems, so expanding interval maps again. And he proves that the following, that if the measure of these ball, if it's, this is something actually, this direction is actually very simple. This you can actually use the ordinary Borel-Cantelli lemma to conclude that if the measures of these balls is finite, then tk of x belongs to this ball for finitely many k. This should be for mu almost every x. So this is the easy part. This you can always prove. This is because that part of the Borel-Cantelli lemma, you don't. Here is the Borel-Cantelli lemma. So this part, the implication going from this line to the upper line, there you don't need independence. It's only in the other direction that you need it. So this you can always prove. But what Kim proved is that if the measure has a sum which diverges, then for almost every point x, you have the following. And he actually proves a little bit more about this thing. Not only does he prove that you have that the iterate, it enters the ball infinitely many times, but that the following holds. If I count how many times this happens between time 1 and n, and this I can write in the following way. I have my ball with center y and radius rk. This is the bk. And I take the indicator function of this set. So this is the function which is 1 if the point I'm plugging into the function is in the set and 0 otherwise. So this is a way to count how many times I land in this ball. And then I normalize this thing by dividing by the sum of the measures of these balls. Or if you like, the sum of the probabilities that tk x belongs to the ball. This is actually equal to 1 as n goes to infinity. So it's a stronger result because it not only says that this sum in the denominator goes to infinity, meaning I hit the ball infinitely many times, but it also tells you something about how often this happens. Because if I have a particular choice of balls, then I can like compute what this sum is from 1 to n, or at least estimate it, and then I get a rough idea of how many times this happens. So since this thing is very similar to what we talked about in the beginning of the talk, where I looked at one point x coming close to itself and not to a fixed point y, it's natural to ask the following question. Do we have for almost every point x the following? That if I just take away this y and put x instead, so you get the following: the ball center x radius rk of tk x, sum from 1 to n, and I divide by the measure of the ball. Do we have that this limit is equal to 1? So the only difference here is that I took away the y and I put x here. So I'm asking the same question about how many times the iterate of the point x comes close to the point x. I'm going to count this thing. So that's the question which I asked myself, and the answer is the following. The answer is yes, at least in some cases. So this is a theorem. It's by myself. It's actually very recently appeared in Studia Mathematica. This year. I'm not going to tell the exact assumptions here, but they are roughly.
Thomas,
yes?
what are you adding in the denominator? Mu of the ball and what?
I mean, the only thing I'm changing in the previous result is that here I have centers y, which do not depend on x. But what I'm doing here is that the centers are x again.
Okay.
So I'm looking at the same kind of counting result, but instead of coming close to a fixed point y for most points x, I'm saying that the point x should come close to itself.
Yeah, and the r, what's the subscript of r? Because I cannot I cannot see very well.
RK, so it's exactly the same thing.
Okay.
Yeah. The only difference here is the x there and the x there.
Yes.
That's the only difference. Otherwise, it's exactly the same.
Yeah, thank you.
Very good. Other questions? So I'm not going to say exactly what the assumptions I have are on the system, but the assumptions will be satisfied by piecewise expanding systems, interval maps, but also other things. So it's not the only system that satisfies this. I need some assumptions. Let me call them mild assumptions on the invariant measure mu. It shouldn't be too crazy, but it doesn't have to be similar to the Lebesgue measure, for instance. And there are some technical assumptions which I think I will not say. So I assume the following. So what I am going to prove, and this, by technical reasons, the formulation will not be exactly like here. The result, let me write the result first, and then I'm going to say the assumption. So the result will be like the limit when n goes to infinity. If I look at this sum from 1 to n, so I'm counting how many times the iterate of x hits a ball of radius rk, and rk depends on x, just as it did in the previous result I was mentioning by myself and my co-authors. So I'm counting how often or how many times this thing tkx comes into this ball, and then I divide by the measure of this ball. So the only thing I changed from the previous page is that here is a fixed rk, but here I assume that rk depends on x. And then I get that this limit is equal to 1 for mu almost every point x. So let me say what is the assumption. Well, I assume that as before, if I say that mk is equal to the measure of this ball, just like before, then I need some lower bound on this thing, and I need a lower bound which is log k to a power of 4 plus epsilon. Epsilon can be any positive number divided by k. So you would, of course, like to have that this sum, when n goes to infinity, should go to infinity, and it certainly does for this thing. But for instance, if I remove the logarithm, this sum will still be infinite, but then it doesn't satisfy this assumption. So I need it to be a little bit more than just divergent. It should be sufficiently quickly divergent. So I have this assumption on the size of the balls, and then you get the result. Yeah, so this is I suppose the last result I'm going to mention. Let me just yeah, I don't have super much time left, so I'm certainly not going to do the proof, but let me just try to explain why in this result and the result with Kirstebulmen Kunde that I mentioned before, there we also had this MK, which had the same definition. Let me just mention why we need to have this seemingly strange way of looking at it. It's just that, well, I'm not going to write a sketch of a proof, but let me just write part of the proof. So this is just to explain or to give an idea of why this is something which helps. But in some sense, I also want to stress that this is a more natural way to look at it, because from the point of view of the measure, the size of the ball it doesn't matter. I mean, the measure doesn't see sizes like a metric size with a metric. It only sees sizes in the measure of a set. So what is important for the measure is the measure of the set, not the radius of the ball. So from the measure's point of view, and this is a measure point of view, the natural thing will be to have balls of a certain measure rather than to have balls of a certain radius. But let me explain why this also simplifies the proof. So in the proof, we are analyzing the following set, the set of points x such that the kth iterate of x belongs to the ball of radius x and rk of x. And what makes this proof here, I mean, the result of this type more difficult than the result of Kim is that when I have if instead of x here as a center, I would have y, then this set is much easier to understand. But now it's more difficult to understand. And what you can prove is that the measure of this set EK, you can prove that this measure is approximately equal to the measure of these balls. And the measure of this ball is constant, so I can just write MK, which is the measure of this ball. It's constant as a function of x, so I can write like this. But to get this proof, I also have to consider things like the measure of EK intersected with EL for K and L different. And you can actually prove that. So if this is just like probabilistic event, what you would like to have is that they are independent. So you would like to have that the measure of their intersection is approximately the same as the product of the measures, meaning that the probability that both these events happen is the product of the probabilities. This is independence. We can prove this. There's a small error here that we can control. But this is the part where it's important that RK depends on X, because this is not true. It turns out it's not true that this holds if RK of X is replaced by just RK, which is not a function of X, but just a fixed number. So many of these techniques to prove things like this requires that you get some control on the independence between EK and EL, or whatever sets you are looking at. But if you don't ask the right question, you will not have this independence, and that destroys a lot of the techniques that you are using. So by introducing this RK of X, then you actually get better estimates, and these estimates makes it possible to prove the results that you like. I think I will stop there, but I can answer questions, of course. Thank you for your attention.
Thank you very much. Let's give our speaker a virtual applause, and let's see if someone has any questions.
I have a question. So I guess so do you know for interval exchange are there like counter examples or do you know what kind of results have been obtained of this kind?
Oh, maybe I should know. I'm usually not working with systems that are not very well mixing. Usually I'm working with systems that, like these systems that I'm talked about, have some kind of decay of correlations that is more or less quick.
I see.
And this is not the case for interval exchange transformation. I think there are results about it, but and I think I know where to look for it, but I cannot say without looking into the literature. There are, yeah.
I mean, I was thinking of more like counter examples because I guess the first result you mentioned by Bochernitz, that one applies to interval exchange.
Exactly, yes.
So then, and the other ones then went like on a different direction. So
yeah.
So I guess
there are. I mean, I know there are some kind of results. I don't remember them by heart, but I can look into it if you like, if you're interested, because I think I know at least some paper which is mentioned a little bit.
Okay.
Yeah.
Yeah. Thanks.
You're welcome.
Are there any further questions?
Do you hear me?
Muy bajito.
Maybe there. Do you hear me there? No.
Yeah,
I didn't hear it very well.
Okay. What about now? Do you hear me?
I can hear you, but it's very distorted, the sound. So it's
No.
difficult. You can also ask a question through the chat, I guess, and then
Maybe. Let me see.
maybe that would.
Just a kind of comment. So the ingredients are always this kind of uniform mixing and.
Se escucha muy raro ahí.
¿Ah?
Es que sí se escucha muy raro.
Ah, caray. Ok.
Okay. Dijo que si lo escribes en el chat.
Okay.
Creo que se escuchaba mejor con los audífonos. Solo.
Is it okay here?
Yeah, now it sounds better. Yes.
Okay. No, it's just a kind of comment. I understand the ingredients.
Now it sounds very bad again. I'm sorry.
no.
Es que se corta, como que hablas y se corta.
What about now? Oh, I'm sorry. So it just was a comment. Forget it. For me, it's not important.
Sorry.
Pues igual, y si lo escribes en el chat y ahorita pues preguntamos.
Mientras pregunte a alguien más.
Yep. So Gallo is going to typeset his questions, and in the meantime, I want to ask a couple of questions.
Okay.
What is that? Do you have like some quantitative version in the sense of there's this Borel-Cantelli lemma by Walter Philipp. He did it in a general setting, but
yes.
he did it for number theoretical dynamical systems, especially bit expansions, continued fractions, and
yes, I remember that. Yes.
So do you have something like in that spirit?
Yeah, I mean, what he proved was basically like what Kim proved, right? But for slightly more restricted systems, if I remember it correctly. He proved this result for like the Gauss map and then some other systems.
All right, and I have a question, another one, which is like in the, I think it was in the later, the one you did with Philip Kunde and Max. Yeah,
Mhm.
yeah, the one in the left, the one in the left.
Yeah.
So have you tried, well, rather than dividing, no, the
Yeah.
other
Okay.
one,
So this thing.
Yeah.
Yeah.
yep, when you have the limit of this quotient tending to 1, the one
Yeah.
with, no, on the right hand side,
Mhm.
up, that one.
Yeah. The result by
ha-
Kim. Yeah.
Yep. So oh, sorry, back him. So have you tried to do something similar, but rather than just taking a fixed point y, like comparing with respect to the orbit of y? So having in the,
Yeah, so actually the result of Kim is actually more general. You can actually have a sequence, a fixed sequence of y.
oh yeah, that's
So in
nice.
particular, you could have you could replace y by the iterates of y if you like.
Oh, that's really nice. That's I ask because I think that also it's quite related to some chaotic stuff, like in the sense of Lee York.
Yeah.
And
that might be the case. Yes. So I mean, the result is more general than I stated, and I mean the result it proves is that you could have a different function than the indicator function. Also, you could have some other function which has bounded variation, and then the same thing is true.
oh, right. Thank you very much.
If the bounded variation norms are uniformly bounded, then it's the same proof. So the short proof of this thing is very short. It's not so difficult. But
yeah, thank you very much. That's great. Now I have the questions. The question of Gallo that we couldn't hear is, what are the main ingredients, mixing and conformality of the measure? What are
yeah,
the
so
other
I don't
measures?
use anything about conformality of the measure. I use a little bit that what I really need, and this is maybe not the main ingredient, but I need some assumption on the measure of balls in general. So I need some kind of estimate that this doesn't become too large. So there should be some positive number s, and so I need some kind of control of measure of balls. And this I need basically because I cannot work with the set EK itself. I have to approximate it by some set which is slightly more well behaved, and then since there are different sets, I need to control a little bit the difference. So this I need, but the main ingredient is really decay of correlation. So what I need is that if I take two functions phi and psi, and I look at this thing, then I mean if n is large, you would expect from mixing that this thing is equal to the product of the integrals. And you need some kind of estimate on how much the deviation is. And you need something like that. This is less or equal to some constant times something which decays exponentially. This is what I'm using heavily. And this certainly doesn't hold for all functions, but it holds if phi is L1 and psi is bounded variation function. So this is the assumption I need. And actually, as long as I have a system which has these properties, then this result that I mentioned is true. So so this is like the real assumption, and it's satisfied for piecewise expanding interval systems. Let me see. What's the yeah? So there are So if you're not in an interval, well, then you're lost. This result is only for interval systems because I'm using this bounded variation thing heavily, but it does hold for other systems like for so it does hold for piecewise expanding system on the interval, but also for some quadratic maps like t of x equal to a times x 1 minus x, where a is the Benedict-Carlson parameter or something like that. So there are various kind of examples. So because of technical reasons here, I'm really using this bounded variation thing a lot. So if you're not in the interval setting, things gets much more complicated. There are other results. So this is like for the last result I mentioned. For previous results, there are some cases where you can prove it for higher dimensional systems and so on, under some assumptions. There are results in my paper with let me see, in this paper with Kielseboom and Kunde from 2021, there are results where we actually get similar kind of statements for linear toral automorphisms and these things. Yeah, there are technical difficulties to get good results in higher dimensional settings.
So
Okay, thanks.
Thanks. So I have just like very one short question. So do you think that if I wanted to prove something similar, say in the context of complex continued fractions, it would be much harder because of this assumption of bounded variation?
Yeah, well, it will certainly be harder. If it's much harder, I am not really able to answer because I'm a little bit. I mean, you have some kind of mixing things for these systems, right? But with what norms? I mean, what kind of functions would you be able to get this for? That's the question. That probably you know better than I do. So
yeah.
But it depends on. I mean, the more functions you can get an estimate of this for, the better it is for you. And so it's a little bit of a question there of what exactly you have.
Yeah, I'll keep it as a future project that some hopefully not so far in future.
Sounds good. Well, like I can mention that I have a new PhD student. He's working for the moment on actually extending this result to like anosov diffeomorphisms and things like that. So it seems that this result, or at least something in the spirit, would hold in for anosov diffeomorphisms. But for there you have to work more because there are more estimates and more difficult estimates to do. But I hope it will be possible. So for the complex continuous fractions, I don't know because I don't know as much about them as you do.
Yep. Well, thank you very much. I don't know if there are other questions for Tomas. Let me check the YouTube transmission. Oh no, yeah, I don't think there are more questions. So let's just.
Yes, no, I have one. So now that you mentioned anosov, so
yeah.
So if you work with mixing SFTs, the measure of maximal entropy will be Bernoulli's. So I guess you can obtain something.
Maybe, but yeah. So the problem is that what kind of mixing control you have, I think, at least for the techniques I'm using.
I see.
Yeah. Well, I never really worked with the interval exchange transformation, so I don't know very well what the properties they have. So I would guess you don't have anything.
I was asking about shifts of finite type.
Subshifts of finite type. Subshifts of finite type. You said. Yeah.
Yes.
Yeah. No. Sure. If you have a yeah. So if yes, exactly. No. If you're working on a subshift of finite type, to me this is basically the same thing as a piecewise expanding interval map with some Markov structure. So certainly yes. I'm sure you could just reformulate this thing that holds for subshifts of finite type that are mixing.
But then when you go to anosov, you can maybe you can codify using a shift of finite type, but so
yeah, maybe. So I mean, the problem here is that it's a little bit exactly what question I'm asking. If I'm just I can certainly do what you suggest. But if I really want a ball here, then what is a ball in the metrical sense? When I put it to the subshift, it will not be a ball anymore. I mean, and so on. So I have different metrics in the subshift and on the manifold or whatever I am in, and it doesn't completely translate to what the ball and so is. So the shape of the sets plays a little bit of a role.
Yeah.
I can certainly get a result like this where I don't have balls, but I have cylinder sets.
Yes.
That's much easier. But if I really want balls, and I would like to have balls because I like them, and then it's a different thing.
Yeah. I see the complication.
Yeah.
Yeah. Thanks.
Okay.
Thank you.
Thank you very much.
Thank you very much. So let's give Thomas an applause. I think we even have emojis for doing that.
Oh.
Please.
Yep. Well, thank you very much. And this invitation is also for Thomas. If you wish to join next week, we're having Neil Manibo. He's in Bielefeld University, and the week after we have Karma Dajani.
Okay.
At the same hour.
Okay.
So,
Yes, but different Zoom links, I suppose.
Yeah, different Zoom links.
Yeah.
Yep. So I may add you to the mailing list if you wish.
Feel free to do so. I'm not promising I'm come, but depends on the subject.
Oh yeah, and if I assume the Christmas dinners are also starting.
Yeah, but it's not as wild as in Denmark. So.
All right. Well, that's good.
Yeah. Very good.
Well, then thank you very much to all of you.